Good afternoon, everyone. We'll start in next 5 minutes. Good afternoon, Santanuda. Good afternoon, Dilip sir. Good afternoon, Chetty sir. Very good morning to you, Neptune sir. You are muted.
I said good morning to all of you. And I am so thankful that you don't arrange these meetings earlier in the day.
Sirshendu, good morning.
Yeah, hello, good afternoon.
Okay. Good afternoon, everyone.
Good afternoon.
I could see so many icons there in the screen. I did not find my one.
Good afternoon, sir. Yeah, good afternoon, sir.
Good afternoon. Anyway.
Maybe you are an iconoclast.
Jyotirmoy, are you there?
Santanuda, yes.
So we can wait for another 5 minutes time or something like that.
Another 2 minutes. I think it's already
okay.
2 minutes past 4.
Okay.
Yeah. How is the weather in Kolkata?
I can't hear you properly.
I said, how is the weather in Kolkata?
Oh, the rain has started.
Oh, that's nice.
It started today.
Professor
Welcome,
Dhruva
sir.
Mukhopadhyay will not be joining today. He has a doctor's appointment. So before we start, I just want to, I hope you all have received the email for RDS 8 in October. Reminder email is also with you.
Yes.
So please, the last date of submitting abstract is 1st July. So I will request you all to please submit your abstract and register. The registration link is also open. And please share the email for the RDS 8, that invitation email, to your contacts as well. That will be great.
And I think every one of us should buy our travel ticket
Yes, please.
at the earliest.
Yes.
দিলীপ তো অন্যদিকে তাকালে হবে না।
Dilip sir has already taken his tickets, I think.
I'm going to attend this time for sure.
Okay.
So
All right, I think let's just start, because it's already 7 minutes past 4.
Okay.
So good afternoon, everyone. Today we have another student presentation, PhD student presentation, and the speaker is Mr. Sirshendu Kumar Biswas. He is a senior research fellow at the Geological Studies Unit of Indian Statistical Institute, Kolkata, and he is currently working in the Western Dharwar Craton. Sirshendu graduated from Durgapur Government College, subsequently master degree from Presidency University, Kolkata. So many of you are his teachers, I assume. And currently he is doing PhD with Trideep. So with this brief introduction, may I invite Sirshendu to deliver his talk on Dykes, outcrop attributes, and magma overpressure. Over to you, Sirshendu.
Thank you very much, sir. So, is my presentation visible here?
Yes, your presentation is visible. Put it in the presentation mode and restart.
Okay. Thank you very much, sir.
I will request all the others to please kindly mute, so that there is no feedback. Yeah, I think everyone else is muted. Go ahead, Sirshendu.
Thank you, sir. And I thank SGT-SGI for giving me this opportunity to present my research on this esteemed platform. And also, I heartily thank all the attendees for their kind interest and time. With that, I shall move on to today's topic, which is dikes, their outcrop attributes, and magma overpressure, as you know. So moving on to dikes, we are quite familiar with dikes. We see such dike outcrops quite everywhere in our geological field trips, and they are basically intrusive bodies, mostly igneous in origin. There are also examples of sedimentary dikes, and they have different kinds of outcrop attributes, but they are sheet-like intrusive shapes with a dimension far reach than the another one is quite common in the field. Now going on to their origins, the particularly intrusive igneous origins, dikes may originate from magma chambers deep down below the surface, and as the magma gradually ascends, they may actually intrude through pre-existing anisotropies present within the country rock, which may be pre-existing fractures or foliations, or the magma may actually create its own path by fracturing the host rock. Now in the second scenario here, we shall focus on this particular one. When the magma actually imparts pressure on its country rocks, and that pressure actually exceeds the tensile strength of the host rock as well as the compressive stress that is subjected to, it actually fractures the host rock, and that fracture is like a tensile fracture here, which we refer to as also mode 1 or opening mode fractures. So particularly this origin we will focus here. Let's look at the mechanisms of mode 1 fractures here. Assume this is a host rock body, undeformed, isotropic homogeneous body, subjected to some tensile stresses acting in this direction, as you can see here. So a tensile fracture will open in this direction, normal to the acting tensile stresses, and as it opens, stresses will actually concentrate at these tips. So much so that with gradual increments in time, let's say at t1 time here, the fracture will actually expand as here the tips will propagate.
Sirshendu.
Yes, sir.
Sirshendu. I'm just asking if Pandian has anything to say. Do you have any issues, Pandian? Okay, I think
We will take questions in the end. If you have questions, Pandian, please hold
Yeah,
it. We will
please
have
hold
the
it.
questions in the end.
Okay.
May I go ahead?
Sure, sure.
Okay, so as I was saying, that with increment in time and as the tensile stresses are still acting, the fracture will actually increase in its shape and size. The shape will constantly remain the same, the size will increase, the tips will propagate, and also it will inflate. So similarly, at some time increment T2, this will somewhat be the fracture shape. And note that it has an elliptical kind of shape here. And this is very characteristic for mode 1 or opening mode fractures. And let's take natural look for dikes. So let's say this is a schematic figure which represents a magma chamber at depth, and a dike is ascending up from it, and there is an outcrop surface here which has cut the dike. So let's take a look at this schematic outcrop shape here and project it on 2D. So you can see that it actually resembles that of an ellipse, irregular, but still resembles that of an ellipse which has a major axis and a minor axis. So let's take some examples from the natural scenario. So on a flat outcrop, you see here's a felsic dike here, and you can see this left-hand side tip here. Then the dike body actually propagates like that. And then on the right-hand side, you can see another tip here. So ideally on a flat outcrop, you see that this is kind of the whole dike shape, complete dike shape, tip to tip, exposed on a flat 2D outcrop surface, which is a very flat ellipse, or we can say it has a very high eccentricity, quite linear to 1. We can also have this evidence in 3D outcrop shapes. This is a dike example from the Canary Island of Spain. And you can see the 3D outcrop shape of a dike here. As you can see that this is quite broad at this portion. As you go gradually up, it is thinning up. And similarly, in the horizontal dimension here on the horizontal outcrop surface, a similar thing can be actually expected. So the shape is kind of an ellipsoid in 3D. And you can see that these section is actually this vertical section here, and on a horizontal cut section, the section will represent like this. So it is kind of a flattened ellipsoid, and either in a vertical section or in a horizontal section, you see this kind of elliptical outcrop shapes, as I have shown in the previous picture. So moving on to the mathematical explanation of this dike shapes, this is the canonical model. So this is my host rock body, which is undeformed, homogeneous, isotropic, infinite, and subjected to some tensile stresses, minus P. Minus is just sign convention for tensile stresses here. So it is expected the fracture will open up in this direction. Now, this is the coordinate system placed upon it, and we have a semi-major axis and semi-minor axis of A and B. And this outcrop shape is actually explained through this mathematical equation long back from Parker. It actually represents here that if we have a point on the dike margin here represented by x and y in the both coordinate directions, then this x and y is related to the host body's Young's modulus and Poisson ratio, and to that of the tensile stress which actually has resulted in its opening. So basically, in case of dikes, let's assume that this is a compressive stress system with a minimum and maximum stress acting on it. So if magma overpressure actually exceeds the value of this sigma 3 or the minimum compressive stress, then effectively the stresses become tensile in nature and the fracture will actually open in this direction. So in this equation, the P term here can be simply replaced by PO, which is actually the overpressure of the magma. And if we rearrange this equation, then see that it takes up the shape or the form of the equation of an ellipse, where the semi-minor axis B is actually represented by this term here. And rearranging this equation gives us the opportunity to estimate the magma overpressure PO from these parameters, which involves the Young's modulus and the Poisson ratio of the host rock, and B by A, which is actually the aspect ratio of the opening mode fracture. So moving on to this particular equation, if we have the elastic moduli of the host rock, which is available in standard handbooks, or even we can have the values through laboratory experiments, then we need another thing, which is actually the dimensions, complete A and B of the mode 1 crack here, referring to Dykes. The thing is, the elastic moduli can always be available, but what if the full dike body is not exposed? So that brings us to a problem. If we have an outcrop shape like this, so this red line here represents the part of the dike which is actually visible in the field. The rest of it is not accessible or actually not visible, maybe it has been obliterated or it has been weathered. So can the overpressure be still estimated from such partial dike exposures? So in today's talk, now we are going to have a look at this particular situation. So let's say that we have an outcrop exposure here of a dike, which actually starts from one tip. This is the visible tip, and the other tip at the other end is actually not visible. So record this outcrop shape of dike. We have taken up the system, the coordinate system, at the visible vertex or the tip of the dike, and at a fixed increment, we measured the respective widths here, something like this. So schematically, the figure becomes something like this. If we take the half widths now, so these measurements on the dike margin gives us the coordinate measurements of the points. Now, this is actually the form, the mathematical form. So you see there are many recorded points on the dike margin, just like this. And since the coordinate systems here, it is positioned at the vertex of the ellipse, the origin, the equation of the ellipse takes up this form, since it has been shifted a distance from the center. So you see we have two unknown variables, a and b, and we have a number of points measured on the dike margin. So taking of any 2 points, we can form two equations and the values of a and b can easily be deduced. The problem arises because in natural scenarios, dike shapes, though they resemble that of an elliptical shape, which we refer to as the mean ellipse, it definitely is very irregular. But there will always be some points, certainly many points, which will actually cross-cut this mean ellipse. So keeping this thing into account, we shall just do some back calculation now. So let's assume that this is our mean ellipse placed in this coordinate system. So the equation takes up this form, similar form, and assume there are 4 points measured on exactly the margin of this mean ellipse here, exactly on the margin, these 4 points. So any combination of two, this two, that two, or any two of them will always deduce a and b values, which will exactly match with this a and b. Now, if we have 4 points such that they are placed at some deviation from that of the mean ellipse, these 4 yellow points here, so a combination of 2 among these will actually produce 6 ellipses, 4c2, 6, and let's have a look at these different 6 ellipses. So this is the first one here, the second one, the third one, the fourth one, the fifth one, and the sixth one. So you see they are creating different ellipses. The trick is when you actually measure the respective a and b for all these 6 ellipses and take up their average value represented by x bar and y bar here, you can see that x bar and y bar actually matches with the actual length and width of the mean ellipse represented by this green ellipse here. So this is the working hypothesis that we take to solve this particular problem of partial exposures having one tip, and taking that into account, we apply this method. So in practical scenarios, what we do is we go to the field and find dike outcrops which have at least one exposed tip, and from that exposed tip, we have incremental measurements of the y coordinates, that is the length, and the respective width. Then we take up the half of this width, so that gives us the x coordinates and the y coordinates. Let's say just we have 50 points here, so we can have a combination of more than 1200 equations forming up here. So that's a lot of equations. We can use an Excel sheet, something like this here, to solve it. And the average value of a and b actually gives us the estimates of the full length and maximum possible width of the dike. And this is the aspect ratio, which we actually need. So to validate the method, we actually tested the hypothesis using some ground data. So this is a map from the Bero region, which is actually within the CGGC, or the Chotanagpur Granite Complex of Purulia. And here are some felsic dike exposures within this CGGC basement rocks. And you see that these tips are visible, which I've also earlier shown you. The thing is that we have recorded about 7 to 8 dikes, which are completely exposed here from tip to tip. A few of them, like 2 or 3 of them, is definitely exposed beyond the confirmed central region. So in effect, they becomes complete exposures. And we have applied the method on partial portions of those dikes to come to results. And these are the results here. So these blue colored logos here represent the measurements of A and B here. And these green logos here represent the calculated ones using the present method. So you can actually see that they have a pretty good close match. And also we validate the method using some previously published data, which was actually published from the Miyake-jima volcano of Japan, there are some arrested non-feeder dikes exposed in the caldera walls of this volcano, which was recorded in Geshi et al. 2010, like that. And Kusumoto et al. 2013, they actually used a nonlinear least square method to estimate complete dike lengths and thicknesses from that. So their results, we have used those results to corroborate ours. So orange one here, the bars represent our method, the calculated results from our method, and the blue ones here from Kusumoto's method. And you can see that they have a pretty good match here. But Kusumoto's method had some limitations, which I will mention later. And that's why this method comes into play. And you can see the range of matching here, length more than 90% here and weight more than 80%. And similarly, for the magma overpressure estimates, they conform in a very good matching line. Now, for the application of the method, we actually look at here the Western Dharwar Craton where I work, particularly in this schist belt, which is known as the Chitradurga Schist Belt of the Western Dharwar Craton, Archean age granite greenstone belt. And this is the geological map of the region. This part is the Chitradurga granite, and in its southern part here in this box, we have some mafic dike exposures. As you can see, these have pretty sharp boundaries with the host rock here linear, and as you can see here narrowing down to this end, ending at a visible tip. So we applied the method here on a few dikes. So compositionally, these are the photomicrographs here of these dikes. You can see pristine olivine crystals, some augites, and some radiating needle-like fibers of plagioclase, which actually radiates out in a consistent direction. So this is a very good example of variolitic texture found in this kind of rocks, and compositionally this is olivine dolerite. So we actually used this formula here since we have the B and A now from the method, and we actually calculated the Young's modulus using this formula, which involves use of the p-wave velocities within the host rock. We have measured it using a portable velocimeter instrument, and this we have used the static Young's modulus value here. So this is actually another formulation which can be used to calculate the magma overpressure, which is actually the summation of the excess pressure, the buoyancy difference, and the differential stress. So even if we don't account for the PE, we can have a rough estimate of PO. Here we can calculate Z, which is actually the depth of origin of the dike, using the difference in between the density of the host rock and the density of the mafic magma into play. So involving all this, we have also calculated some stress intensity factors of the host granite, and also we can calculate the stress concentrations at the dike tips. So these are the results of the study, and you can see a minimum value of about 27 MPa and going up to 73 MPa for the dikes here, with a corresponding depth of about 10 kilometers to 25 kilometers, and corresponding range of quite high fracture toughness of the host granite. So this involves the present method and the results. Now going to the second part here, we also encounter very often dike shapes which differ considerably from those of the linear or the elliptical outcrop shapes. As you can see here, these are shapes which have offsets here, a systematic one, or like that, or you can have different dike shapes which are quite curvy, which have protrusions branching out like that. So the question is, the canonical model doesn't account for the creation of such shapes. So what leads to the formation of these kind of dike shapes? So just let's have a recap at the modes of fracture formation here. We already talked about this opening mode of fractures, but other than the opening mode, there are two other modes. So the shearing mode here involves actually shearing along the propagating dike line here. You can see the line of fracture propagation here, and the plane which contains this line is the plane on which the shear is being imparted now. So this here, the displacement is along this line, del U represented here, and you can see that this del U is actually perpendicular to the edges of the fracture wall. And conversely, here you can see that shearing is taking place on this plane, and the line of fracture propagation is actually normal to this plane. So effectively, here the displacement del U is actually along the edge of the fracture walls. So respectively, this is known as a shearing mode, and this is known as the tearing mode of fractures. This can be actually utilized. Let's see, this is the mode 1 fracturing here, and you see this is the tensile stress acting in the direction, and these are the compressive stresses here. So if the stress axis rotate, let's say here the stress axis is rotating, as you can see here on this particular plane. So now in response of the rotated state of stress, the dike tip can simply turn towards the new sigma, greater sigma max axis, which is acting on this plane. So this gives a juxtaposition of mode 1 and mode 2. So this kind of dike shapes can be expected when a mixing mode 1-2 occurs. And you can have natural examples like this, carved dike tips. Also, a mixing mode of 1 and 3 is possible. Here, the advancing dike here, the dike is advancing in this direction. So the line of propagation is normal to the plane on which the shear is resolved, and that results in tearing mode fracture, or here offsetting. So the shear is imparted along the dike body and it is getting offset like this. So this is a mode 1-3 mixture, and we can have a mixture of all three modes here, 1, 2, 3. Going on to the natural examples. Now you see in a mode 1-3 mixture dikes, the dike should have an opening displacement component here starting as a mode 1 fracture. Now as it ascends, the stress state may change, or the orientation of the principal stress axis may rotate, which results in shear being imparted along its body. Now if conditions are ductile, the dike body may actually accommodate the shear and it may get bent in such a geometry. Now as it continues to ascend and magma supply is still extant, the dike will protrude tips from its outward margins, saying this is actually the line along which the sigma max is acting now. And as it gradually ascends upwards, it may get into offsets here, which actually is connected down at depth, but at the surface they might not be connected. But the offset pattern is always systematic, and you can see in this diagram that this angle, at the angle through which the sigma max axis is getting rotated, represented by theta here, is known as the twist angle here, since the dike body is getting twisted in response of this rotation. So this kind of dike geometries is actually visible in the field. You can see a systematic continuous pattern of bend or curvature in the dike body. So along these junctures here, you can see that some new kind of fractures are getting formed. I shall show you some zoomed in versions here. So you see as the dike body is getting bent and it is getting twisted, along these portions, the fractures are getting created and the dike body will get separated in a next time interval here, resulting in offset geometries like this. So let's have a look at the comprehensive sequence of mode 1-3 loading. So this is the first scenario where the dike body has formed in response to some tensile stresses here. So this is actually the sigma max axis, and this is a sigma min axis which has been exceeded by the tensile by the magma overpressure. Now you see if sigma max rotate clockwise in this direction and conditions are ductile, as this is represented here, depth. So you see that the dike body is getting bent in response to the imposed shear. Now as it propagates, since the sigma max axis is still acting in this direction, and now the sigma min axis is in this direction, slide, and as it moves upward, the segments may actually get detached. Now as they get detached, they are still continuing to evolve since magma supply is extant. So actually they will try to get connected by the formation of bridges. This kind of examples are also possible, where segments are actually connected through bridges. Or they might not get connected, but the advancing tips will actually turn towards each other due to strong mechanical interaction which is happening between them, because these segments are actually overlapping. If they don't overlap, then such kind of curvatures may also not occur. Now you see, whenever such curvature occurs, then again, due to the still ambient sigma max axis acting in this direction, dike tips will protrude out from the outer margin. Now you see these are also dike horns, but these horns are not like this. These are a second generation of horns, odd and second order of horns. So we refer to these horns as the first order dike horns and this kind of horns as the second order. Now this will be more clear from natural examples here. So this is a sequence of n echelon dike segments which result a felsic vein actually here. Or you can also have an example of dikes. Very beautiful picture of systematically arranged segments. Let's have a look at this one first. So if you just look carefully at one end, you see that respective segments are actually offset towards the right side of this one here. So this is a dextral kind of offset segment here, discontinuous. But one segment here, as is shown on the traced diagram, you see that this has been breached. And here are some second order horns coming out of it. Now I'll show you some more pictures. So this is like a felsic vein, which is continuous in nature. And from the outward margin, you can see that the horns are protruding. Another example here, this dike body here is continuous, but bent. And that results in the protrusion, in the formation of protrusions or dike horns from their outer margins. These are more beautiful examples of some mafic dikes here. You see horn protruding here from one end, similarly here. And in this diagram, you can see, this is the earlier one, these are breached dike segments. So these two segments have actually been detached, and due to mechanical interaction between them here and extant magma supply, they have been linked up now. You can see that there are vestiges of the host rock still present in between them. So such features enable us to distinguish in between continuously curved dike segments and segments which have been breached later. Here is an example of second order dikes. You can see two detached segments. The tips have turned towards each other due to mechanical interaction. This is the turn tip, and as the tip has turned, you can see a horn of second order protruding out from its outer margin. Similarly here also. So several orders of dike formation, like horn formation, are actually possible. You can also see examples of felsic veins here, second order horns. So this is one school of thought, but horns have also been described as failed dike paths. There's another school of thought. Keeping that in mind also, we actually utilized a method to estimate the aspect ratio from dike horns. So let's assume this is the hypothetical scenario where we have a dike tip to tip. This is the horn here. So this is the length of the horn from the exposed tip of the dike to that of the horn. But we don't know the width here. So we can easily solve for the width here, since if you can place our coordinate system here and take some measurements of the horn margins using the similar method, we already have this A value here. We can simply solve it for B. And with this method, we applied it on some mafic horns present within a dike in a particular location. As you can see here, these horns, our tips are exposed. So the results indicate a very interesting phenomenon here, that the aspect ratios as measured from the horns actually are in order with that of the whole dike body, as you can see here. So this enables us to have a possibility of using dike horns as proxies for effectively estimating their aspect ratios and thereby their magma overpressures. So summing up the whole thing, here we have development of a new method for estimating aspect ratio and thereby the magma overpressure from partial dike exposures featuring one tip. Validation of the method has been done both in ground and against published results. Then we have applied the method to some mafic dikes found within the Chitradurga granite of Western Dharwar Craton of India. And then the obtained aspect ratios have been utilized to calculate the magma overpressures, depth of origin, and also the fracture toughness of the host granite. Then we have utilized existing concepts of mixed mode loading to understand emplacement mechanisms under mixed mode loadings and their characteristic outcrop patterns, which differ from that of mode 1 opening. And we have established a progressive spatiotemporal evolution of dikes under mixed mode 1-3 loading, and therein we can distinguish in between incremental orders of dike horn formation, and we can have now the possibility of using dike horns as effective proxies for estimating dike aspect ratios and thereby their magma overpressures. So that will be the summing up of this whole thing. If you want details, you can look at this paper which has been published recently. And for using the method, you can actually use this code developed by us, and this is actually available in my GitHub page. That will be all for today. My acknowledgements, and I shall take this opportunity to acknowledge late Professor Dilip Shaha, who have greatly inspired us and helped us to take up this work at the initial stage. And thanks to my supervisor and my colleagues here and my co-workers. This is the team that I work with. Thank you very much for your attention. Any questions, comments are welcome. Thank you.
Thank you very much, Sirshendu. It's very nicely explained, and I'm really happy the way you presented your seminar. It's very very clearly presented, very nice set of slides, and you almost spoke like a teacher. Very nice.
Thank you, sir.
So I'll just start the question answer session, then I will hand out to other audience.
Sure.
So when you spoke about the interaction between different dike segments and the interpretations that you have drawn, are
Yes.
they based on any modeling, or how you have constrained these?
Yes. Two things.
And, propagation.
Yes, mainly we have two proxies. One is field examples. I have presented like 3 or 4 pictures here. We have more pictures. Like in every single outcrop that we have seen, which records such offset segments which have overlapped. In every single case, as you can see here, the overlapping segment tips always they turn towards each other. Now, this has been also explained in one previous work in Owenberger et al. 2000, I think. They have used a damage geology model, and therein also their simulation results corroborate to this fact that whenever strong mutual interactions occur, then advancing dike segment tips will actually turn towards each other.
So you have not done any modeling as per se that
No.
okay.
Till this
Okay.
point of time, we have not undertaken.
Okay. So the progressive deformation that you are proposing is more like a speculation.
It's not a speculation. We have field evidences supporting that, but definitely it's a schematic one, and some kind of modeling work will definitely like strengthen the fact that it actually happens so, and it can give us better insights, definitely. And we are trying to do that, but at this point of time, we have not been still able to do that. We're trying.
And all the final thing that I want to ask you,
Yes.
it often looks like the situation of riddle shears. So, have you considered any strong strike slip component while you thought about, the coalescence of these individual dike segments?
The thing is, this is a very like a very systematic pattern. If you see this particular image here also, you see that the curvature of the dike body, here it is a continuous body. And this continuous curve geometry can be very simplistically, but still generally constrained way, be explained by the shearing of a dike body in a particular direction, stresses acting on it. Now, riddle shears can definitely be a factor in more complex scenarios, but the simplest explanation for this thing is the one that I have shown you right now. But in some scenarios, definitely there can be interactions in between riddle shears and the ascending dike bodies.
No, actually, some of our observations were that if there are two parallel segments, and if they want to interact, generally, if you have a overlap, it's more difficult to make them interacting. Rather than if you have an underlap, that is a favorable situation for two segments to interact, essentially in a tensile regime. So I don't know if you also observed similar situation.
Okay, I should be very happy, sir, if you can show me some pictures that will actually give me some more insights in it, and I can work on that.
Okay, thank you very much. I open it up for others to ask questions. Thank you. Thank you.
Jyotirmoyda.
Yes, Tridip. Yes, go ahead.
If you allow, I can say something about this riddle shear particular that part actually. Yeah, it's possible. What you have mentioned is possible, but whatever Sirshendu has mentioned in that particular figures or these field photographs, we have not encountered any kind of riddle shearing. So definitely, whatever you have mentioned, that it's a possibility. more complex scenario. But here we have not, encountered any kind of any evidences of radial sharing.
Okay. Thank you.
Oh, thank you, thank you.
So if anyone has any more question, please.
Or any suggestions.
I think some young students should ask something. This is very interesting talk. Okay. I think somebody are really thinking to ask something. In the meantime, I should.
We
talk.
have a question in the chat box.
Does this moderator Chayan Maite? Yes, Sirshendu, you can go ahead with this question.
Okay, so for this question, dikes are like mostly vertical to subvertical. So technically subvertical to vertical geometries. This model is definitely applicable to all kind of subvertical and vertical geometries. And as for the other end member, there is the horizontal ones. Those are not dikes. They are mostly seals. And if we have like branching out dike geometries, then also the fundamentals of this model are applicable, but definitely wherever the branches are, the ambient stress system will act accordingly on those branches. But the whole model is actually established considering the ideal scenario where the dike body is vertically ascending. So it's mostly like that.
Okay.
Thank you.
Yes, Shantanuda, you had some questions.
Now, I must congratulate Sirshendu. It was a very nice talk and very nicely explained.
Thank you, sir.
Sirshendu, just a query. So the main objective of your work is to say that the fluid pressure, I mean the pressure, overpressure that has been generated by the magma from where this dike has been emplaced, or the dike material, is that correct?
Yeah, the first part of the talk deals with that, estimating the magnitude of mode dike formations.
Okay. So in that case, you have already considered that the rock in which the dike is emplaced is isotopic in nature, right?
Yeah, and in the field scenario, we have granite, so kind of we have been able to use that hypothetical model here.
No, it's fine. So the thing is, in your some of the graph, I have seen that your fluid pressure varies from some 65 to 76, and other I have not recorded. So
I can show results here, maybe.
From here, yeah.
So this slide, I think.
And this slide one, another slide you have shown is varied from.
Yeah, this one, Sirshendu, this one.
Yes, there are some values.
Yeah, it's a variation in the fluid pressure, right?
Yes,
and
yes.
All this fluid pressure is giving you the same aspect ratio of the dike?
No, definitely not. As you can see here, these are the aspect ratios. Yeah. So definitely for aspect ratio of, here it is 0.002, since it is B by A, you can see like a lesser aspect ratio, so lesser overpressure, lesser depth, and then higher aspect ratio, higher overpressure, higher depth. Okay. I mean, greater depth.
Fine. So the thing is, for the same dike, if I think that there are different overpressure at different parts.
Okay.
So how do you account for that?
Okay, the thing is, when we are considering this canonical model, it has like 6 fundamental assumptions, and one basic assumption within that is that the fracture or the crack is loaded by a uniform internal pressure. So this model doesn't account for variable overpressures acting in the formation of a opening mode crack.
So what does this means then? PO value variation of PO value?
in practical scenarios, variation of pure values is actually very plausible. Since we have a magma chamber at depth, then we have a host rock which will have inherent heterogeneities within it. Then there will be fluctuations in magma generations also. So definitely there will be variation in overpressure values, but uh, summing it up, the whole scenario,
But it is
if
including in the same type of rock, no?
yes, in the same type of rock, but if the overpressure varies, then this canonical model will
And,
not hold.
and your measurement is you are working on an area. I think from the pictures that you have shown, it's around maximum up to 1 square kilometer. I can say, not more than that.
I have shown some. No, it is a bit more than that, but oh yeah, nearly 1 square
Yeah.
kilometer.
So in 1 square kilometer, I can think that the mechanical property of the rock and other things are almost similar, right?
Yes. The
But
thing is to explain that.
yeah, just to know how this how you account for this variation of the fluid pressure.
Yes. I will definitely come to that, sir. Here you can see that there are dikes which have been numbered as 162, 162, and some 161, 161. So these are two different locations actually. So this I have not incorporated into this top. Actually, one location, this 161 here, you can see that the aspect ratios are a bit on the higher side, 0.005 to 0.006.
Yeah.
And these dike are kind of like more thick, and they have a continuous bend geometry sometimes. So what we have been able to record from the field, it suggests that they are a different generation of dike compared to that of this CH162 here, which are, we presume that they are a newer generation of dikes. So there is a time variation in between their formations. So the older dikes have actually been the results of a bit higher overpressure. Yes, and the younger ones resulted from a bit lower overpressure values, which is actually possible because these are results from shallower magma chambers resulting in lesser overpressure values.
Now, what is the time frame that you are talking about in millenniums? No.
Actually, this diking event is at the top. These are the younger granites sitting at the top of the stratigraphic level, and these granites have been included by the mafic dikes. So definitely the granite emplacement age is around 2.61 giga-annum. So emplacement of these dikes are like just after that, within say around
No, no.
2.6
What I mean to say is that the different segment of the dike are of different time. You are saying like that, right?
No, sir, not the different segments. I'm saying that these two locations have dikes which are of different generations.
Okay. But you are saying that you are predicting that they are from the same magma chamber.
No, not the same magma chamber. One is from a magma chamber at a greater depth, and that resulted in some greater overpressures, and the other may be from a shallower depth, which have a comparatively lesser magma overpressure.
You can have a shallower pool of magma
Yes, definitely. That is also
from
possible. We can have a shallower pool.
from the deeper level pool as well.
Definitely,
You can
definitely,
form a secondary pool as well, right?
definitely.
So the
We cannot
source could be
constrain that.
similar.
Yes, definitely it is possible. We cannot constrain that totally, but definitely it is a possibility.
Okay. Okay. So if in an area, if I find several dikes of giving several data like this that you have shown, how will you explain this? You'll be saying that they are of different times
No,
or
only
different
seeing the
generations?
values. Only seeing the values, I will not comment on anything. I will try to look at the actual outcrops, the geometries, the stress history of the terrain, any geophysical data if available, and gathering all that up. Then only anyone will be able to comment
So
on something.
you were saying that from the two different locations, these dikes are not connected.
No, definitely not connected at depth. These dikes are, the two location dikes are definitely not connected, but they can be result of a shallower pool of magma chamber which can have a conduit linked up to a deeper source at depth.
Okay. So another thing that I want to discuss,
Yes,
you have said that there is a rotation of stress axis.
yeah.
How could you do that?
Yeah, the dike geometry actually is suggestive of such a phenomenon. If I can go back to this picture here.
And that is the interpretation.
Yes, definitely. That's the interpretation. Yes, sir.
That's the interpretation. It's your interpretation, right?
Yes.
But the thing is, how could you change the stress axis unless and until you change the plate kinematics?
Yeah. Actually, in this region that this Chitradurga Schist Belt, the Dykes have recorded, there are like 3 deformation events established. The first one is D1, D2, which is actually coaxial. So I'm just saying it together. And that acts in a northeast southwest direction, roughly speaking. And then there is a D3 deformation later phase, which actually is a rotation. And it acts in a mostly east-west to east-southeast, west-northwest kind of direction. So rotation of stress axis. Yes, sir.
Just
Yes.
let me tell you one thing. Right now, if I think about the active zone, right now, if I talk about the active zone, including Shingum shear zone,
Okay.
the compression direction is uniformly from one side. For example, if I give you the example of Himalaya, it is from north-south. Okay.
Okay.
Tentatively north-south. It's not north-south, not north-east. But you also have evidence of east-west compression. We don't see that. There is no compression axis you can really achieve from east and west direction. But we see some sort of evidences from fracturing as well as from our other ductile structures. We could see that there is a east-west compression.
Okay.
Okay. So the thing is from different episodes of deformation, you can have this, but it can. But for example, why I have given the example of Himalaya, because we know that the stress axis is uniform here. You can have different type of things, but can you really do this without changing the stress axis? Because your stress axis has rotated. What I have understood, right?
Yes, definitely. That helps.
Rotated. That rotation should be, I think it can only happen if you have shearing.
Definitely. I mean, the rotated
Otherwise,
axis.
the sigma, your direction. In fact, even if you have a simple shear deformation, you cannot rotate the sigma 1 axis. So how could you really rotate it? That's the main, I don't know, but we must think on it. I don't have any answer for that.
Rotation of the stress axis, sir.
Yeah.
Yes.
Right at this point.
Okay,
But it's
sure.
very interesting. I think many line of thoughts will come up from your study, and some young people are waiting to ask you many things. Ayan is there. Ayan, please go ahead. Thank you very much, Sirshendu.
Yes.
Sirshendu,
Thank you.
sir, Shantanu
Yes,
sir.
sir.
हाँ बोलो. Yes.
Sirshendu, Shandip sir here.
Oh,
Yes, sir. Please.
Yeah. I'd like to make a few comments related to Shantanu sir's queries. The first of all, like Shantanu sir was saying, that you could have also mentioned that your magma overpressure are always your function of your aspect ratio. So that's why your magma overpressure has a range. Otherwise, it would have been a single value.
Yeah, as I shown in the results.
That I have understood.
Right.
That I have seen.
Right, sir. Now, the second thing related to this is that, related to mainly petrological aspect, specifically from the dikes of the Dharwar Craton, be it the eastern Dharwar Craton or the western Dharwar Craton, and that also it's a matter of discussion as well, and that will also compel me to ask the second question. But first, to clear this up, there are different ages of dikes.
Yes.
At least 9 ages of dikes are available, both in the eastern Dharwar Craton. Some are actually not present in the western one, but in the eastern Dharwar Craton, total 9 mafic dike swamps are available. So now the related problem is that there are several orientations in which the age or the age of the dike is actually same. So you can't really differentiate that which is your 2.37 GA dike and which is your 1.89 dike. that is a bigger problem than this. So the geometry you are looking at, that is definitely that is based on field evidences, and that is really good. There is no question about your geometry, but the problem is about the age. Okay, and apart from that, like Shantanu sir was saying, there have been reports, both geochemical and recent some structural reports from our group as well, specifically in the Eastern Dharwar Craton, that there are not only a single magma chamber, or there is not a, means you can say, there could be more than 3 or 4 shallow chambers as well, from which your dikes can get their supply.
Definitely.
And apart from that, again, the related problem is also there, that most of these dikes, again, from both structural constraints, AMS constraints, it has been shown earlier as well, that most of them, they also have a lateral injection.
True.
So, I don't know, means, actually, I missed your first 15 minutes because I was traveling. So I don't know whether you have discussed that aspect as well. I don't really know, but I think the parameters like the flow of the magma laterally, the flow of magma vertically, as well as, like, I think Jyotirma that was also telling something related to this, and like I was mentioning about the query by Shantanu sir about the depths of the different chambers. So I think just a suggestion from my side that you can look at the geochemical data as well. Means I'll not suggest you to go, or it is not always possible to interpret the each and every, means you can say the weight percentage of each and every oxide or every other chemical constituent. But overall, you can look into that, and then you can have an idea as well from that.
Definitely, sir.
Okay, so the problem of lateral injection and vertical injection, because your model is, I think, mainly based on the vertical injection, from where I picked up your talk. Mainly it is relying on vertical injection, but there are also several evidences of lateral injection. So how your model is also fitting into that, you can, if you want, you can try to look into that.
Definitely, sir. Thank you for the comment. I will look into it. Definitely.
For your suggestion. And I think Ayan is there. Ayan Pakistan.
Oh, okay. Yeah. Ayan has raised his hand.
Okay, so Sirshendu, the excellent talk. Now, I have one query regarding your talk, but I will come back to it later. Now, coming to Shantanu sir, as Shantanu sir said that it is hard to reorient the stress axis in orogenic belts and so that. But I have a query, Shantanu sir, like in the picture Sirshendu is showing, here the stress axis get rotated at the tip of the fractures of such, in such a small scale, such kind of stress reorientation can happen. I mean, it is quite common if you see that.
True. So, that is what I wanted to know from him. Whether he has considered this tip axis, this tip stress, or he is talking about the tectonic stress component.
Both these scenarios are actually possible. I missed that point here. But definitely, local changes of stress axis, as Ayan said here, is definitely a possibility.
Yeah, Ayan. Thank you.
Okay, so now Sirshendu, can you go to the last part of your talk where you showed that the horns can also be, used to estimate overpressure?
Okay, I'll go to that. You want to see this model?
Yes.
Okay,
so, now, as much as I know from your canonical model, that model can be used to estimate overpressure only when the fracture is mode 1. But when it comes to the horns, there are some shear components across the or along the fracture. So in that case, how are you using the canonical model here?
Really good question, and thank you for asking this one. See, there are two contrasting school of thoughts, and I have explained the first school of thought here, which says that horns are actually protrusions radiating out from the outward margin of shear dike margins actually. So definitely considering that school of thought, horns are always a result of shearing, and it definitely involves some other components other than the opening mode. But there is then another school of thought, as you can see in this slide here, and they prescribe that horns are actually failed dike paths, and they are not always located at these outward margins of curved dike segments. You can have horns at many other portions of the dike also, and it actually occurs when the part of the dike finds a weaker path for its propagation. So considering this school of thought, we actually tried, so if the dike body is actually propagating like that of an horn, let's see what is the aspect ratio for those horns. And considering that model, we did that. The interesting finding is, it showed that whenever we have aspect ratios of dikes, like horns I mean, they are in order with that of the actual dikes. So this actually opens up this possibility. We still have work left. We need to, if you want to establish this, or if you want to nullify this, in any case, we have to take measurements of many horns, which are actually results of shearing, which are not results of shearing, and then we have to tally them up. But this opens up this possibility of using horns as estimators of aspect ratios.
Okay. Thank you.
Yeah, thank you. A very good question. Thank you.
Yes, Neptune sir, go ahead.
Firstly, I must congratulate you and your advisor too for a wonderful piece of work. This was very impressive,
Thank you.
and you presented it so well also. I have one or two questions and observations. Firstly, I was thinking, your method, one very good place for its application would be the Bundelkhand Craton. I remember from 50 years back, Amitabh Bagchi did his field work there and showed that 3 directions of dikes of different compositions. So first I thought these were just conjugate joint sets, but why the composition will change, that's interesting. The other thing about Santanu's observations, I was just wondering, you said that the sigma 1 direction is more or less constant in the Himalayas. But if we look at the long-term history, firstly, the direction of movement of the Indian plate has changed from northeast to north-south. And even then, see, when the subduction is going on, the collision is going on, your sigma 1 is almost north-south. And then when the thrusting took place, when there's an overburden, then sigma 1 is possibly vertical. I was just wondering, wouldn't that change with an evolving geological situation? That's it.
Are you asking me?
Yes, you too, and both of you actually. Yeah.
Okay. For me, I think you are right. If you increase the elevation of the Himalaya, but we must remember also that there are erosions are also going on at a very active rate. So now the calculation says that the sigma 1 is almost horizontal and it's tending towards northeast, around 20 degree, around 20 degree. So it is. We can say that this is almost uniform in nature, at least with the onset of suturing. But prior to that, you were talking about the earlier part from the Cretaceous, right?
Mm-hmm.
From 130 million years back.
Yeah.
But the Himalaya did not form then. Himalaya formed only in 50 million years ago.
No, Himalaya did not form then, but we had the rocks that formed the Himalayas formed then. And at 130 million years, by all geological evidences, we had rifting going on there, where the Lhasa block was rifting away from the Gondwana land. And of course, the rift will have its own set of sigmas and own set of stress geometries.
And that will be another stress axis altogether. And that will be evidence from the paramagnetic data and the dike orientations and everything. But
exactly. So yeah, but within the Himalayas, we have rocks and dikes from that age also. That's what I was telling you.
Yeah, true. That is fine. But I was talking about that thing. But now you have also understood that from in the outcrop scale, the stress axis can also, because it happens also in the porphyroclast. Porphyroclast tail structure, this thing happens. That tail geometry can vary with the shear.
Okay. Mm-hmm.
There are a lot of work in this since 2000. And Shantanu Mishra has a very nice work on this, how the tail geometry propagate. Sometimes what Jyotirmay was sometimes saying, that overlapping or underlapping, there are so many criteria to answer that. But anyway, now if Sirshendu has anything to say about it.
Definitely, sir. I totally agree with the notion. The thing is, local changes are possible. There are reasons behind that. Like one paper, Foley et al., 1989, I think they have cited the reason of local heterogeneities within the host rocks or the wall rocks, actually, that can locally perturb the stress state. And there can be many other reasons like that. There is one paper, I don't remember at this point of time, they say that the ascent of dike itself is the reason of local changes in stress axis. So within a local areal extent, changes in stress state is quite possible, and always like constraining each set of change and why that happens is really difficult. But such changes are plausible, and evidences of such changes are always recorded in geological bodies like this. So yeah.
Sirshendu, I don't know if you are familiar with it, but my group also has worked substantially on these aspects of dikes. I don't know if you have read any of the papers on
I have seen
the
some of
different
the
dikes.
posters in the conferences, sir, definitely. I know that you are working on dikes.
Yeah, so we have, you can look at 3 papers. We have published one in Pachmari dikes, one in the Pune-Nasik dike, and the other one is in the in the Nandurbar Dhule dike. So all the big dike swarms in Deccan we have covered, and we have exactly looked at this aspect ratio, right? And to calculate overpressure. Now, one of the things our observation is, if you analyze it in a larger scale, right, where you calculate, I mean, the dikes are of kilometers length,
Yes.
and then it's very difficult to constrain, to be honest, how to measure the length. You measure the length from the satellite image, you measure the thickness at the in the field. But so, I mean, there is a mix up of data, but if you want to analyze a dike swarm, that is what you have to do. But having said that, with all the constraints what we have observed in all the dike swarms, the length by thickness or length by width, whatever you say, is not linear. And it has a very wide spread. If you want to fit a linear trend, it's like the R-square value is 0.3, 0.2, like that. So there is no linearity at all if you want to do that exercise at a regional scale, if I put it that way, right? So one of the things that people try to, advocate as a reason for that is thermal erosion. That the width, whatever you measure at the surface, is not representative of the true fracture width. So the width has subsequently changed due to thermal erosion. So one of the things that I will suggest, if because you were also looking at this aspect, that try to investigate, why don't we actually see whether is the thermal erosion only reason, or there are other reasons. I mean, there is also, of course, the reason of your measurement problems. But having said that, I mean, even if you have that sort of measurement problem, but why it doesn't follow any trend, right, at a regional scale? It should ideally follow, right? Like you have shown for 2-3 dikes or like a smaller area, as you are seeing, B by A has a linear trend. If it is a same generation of dike, but that is something that we don't observe at the regional scale. So that is something I will encourage you to look into, why it doesn't happen, right? So that will really help us.
Really, sir. Can I ask one thing? Sorry, saying something. Sure.
Yeah.
Yes, you are right. That for a large dike, that A by B relation they're not linearly related. But if it is a purely mode 1 crack, then the linearity would be there. Okay. So whatever you are telling, that's a large scale, yes, it's true, but it's possible that at the end of the dike emplacement, probably there are the mixed mode condition or any shearing condition. So that may affect. But if it is there are papers, I can't remember the exact reference now, but they say that if you have purely mode 1 crack, then there will be a linear relationship between A and B, as the length and width ratio. So
no, I agree with you, but I mean, if you look at Deccan dikes, I mean, they are, dominantly mode 1 cracks. They are not.
I have seen the data. Yes, I have seen.
So I have
they are dominantly mode 1 crack, and repeatedly they do not follow the trend. So I will encourage, if you can look at it. I mean, this will help us as well.
Exactly.
So and the other thing, I think with the discussion that was happening around the stress reorientation at the crack tip, etc. I think as these are progressive deformation, what would really make your hypothesis very strong if you can do some analog or numerical modeling. I mean, that would definitely strengthen your research, and you will give some very definite answers. I mean, you can actually demonstrate, if you can make a ANSYS or an abacus model, you will be able to show that at the tip how the crack propagates, or how the stress orientation locally changes.
Yes, thank you for this suggestion, particularly the modeling part. We are trying, but till now we have not done anything related to the modeling part. But there are some numerical modeling, particularly on that segmented dike. So they got the similar results, particularly for this what Sirshendu has told. So, but you rightly pointed out that okay, we need to do some analog or numerical at least that will definitely strengthen that, I believe.
Okay. Sir, I had a question. Can I ask something?
Yes, of course.
Yeah, sir. Actually, when you measured these aspect ratios of these very large scale dikes, kilometer scales, I mean, how did you confirm the ends of the dike? Like, were those ends visible in the field or from satellite data?
No, I mean, if a dike is you have dikes which are 50 kilometers long, right? In Deccan, yes. They are really long. So you cannot really. So the dikes are also, sometimes they outcrop, sometimes they go underground, and you will not be able to see the tip. So what you generally do, you essentially try to figure out the tip from the satellite image, and you kind of take the width at the middle of the dike. So that is what you can do. That is the most approximate pragmatic approach that you can take, and that's what we have followed.
So one problem that may yes, sir, please complete then.
So I mean, I understand there is problem in the I mean, it's not exactly like a laboratory where you were, but that's the nature of it, right?
Yeah, sure.
There is some contribution from the measurement bias, there is some contribution to the thermal dilution, but with all the constraints, I mean, even if that is there, I mean, we should see some trend. We do not see any trend. So that is something I will be good if you can look at.
Definitely, yes, I will try to look into that. Yeah.
Sirshendu?
Yes, sir.
One last query I have. Long back, I think Shantanu sir has also seen that during our field work. Pradeep might have also seen that. There are some dikes in the Shubhanrekha riverbank near Galuri and Ghatshila. They simply look like that they are very tight, dexterally or sinistrally folded in nature. So it is very unlikely of a dike to get folded like that. But I don't know. Could be possible as well. I don't know any reason for that. So is there a for your different combinations of modes? Is there any combination from your different modes of this fracturing and dike emplacement that you can corroborate that it is looking like a folded one, but actually it is not a folded one?
Okay, I get your question, sir. I have not seen. I personally have never seen folded dikes. So I don't know the outcrop geometry. But as I can gather from your question, apparently folded geometries are apparent visible at least. So as you can see,
right.
I will show you this one.
You have also shown, I think, one
I think this one here
field photograph. Yeah, but this is, I'll say this is, if I say that this is a folded one, this is kind of an open one.
Yes.
But I am talking about very tightly folded one.
I have never seen very tightly folded dikes. That might be definitely possible. I have not seen. But open folded dike
No, those who have visited this place for our field, I think Sridhar has also done field work there during our MSc days. I have also done with Shantanu sir himself. We have done field work over there. So there are exposures like that, which are referred to as the newer dolerite dikes of the Sindhu.
Okay. So is it a result of like later deformation? Maybe not related
I
to
don't know. I don't know. Means at that time, I was not looking into that, but I have some photographs with me. Later I can send it to you. You can look at that and you can find a possible solution that whether they are just looking like that, and you can explain with your some combination of your modes.
Thank you, Shandip. I can remember that exposure.
Yeah.
There are dikes, but they are highly sheared, and it's true.
Right, highly sheared. So that's why I don't know whether they are itself they are folded or they look like they are.
Really, I don't know.
Folded, I don't know. I don't know also.
Really, I don't have an answer now. But definitely, when you...
I'll send you the photographs.
Yeah, sure.
You can again look at it. Yeah.
So you think in this...
because he is working on this aspect. So maybe some of his combination can explain this.
Yeah, definitely. And regarding Shantanu sir's question, I'd like to add two things. That in the Western Dharwar Craton, yes, Sandeep has already mentioned that there are different generations of diking even in the Eastern Dharwar Craton as well in Western Dharwar Craton. So in the Western Dharwar Craton, the dike age ranges from 2.37 to 1.79 GA roughly. So in between these two ages, there are a lot of diking events. And regarding this stress axis changes, there are two possibilities if I can make a summary. So that is, one is the local stress that's acting at the tip of the dike, and the second is the regional one. For the Chitradurga dike, whatever we have observed, the regional stress field has a role. So that we have not worked out concretely, but whatever we have seen so far, the stress axis changes, the rotation, that actually are in a good agreement with this stress axis changes, whatever friction they are shown in the dike. So that's I wanted to add this thing.
So Trideep,
yes,
I'm just I have I mean, it's, what interest to know.
Yeah, sure.
That when the dike are getting young and young,
yes,
the value of fluid pressure reduces.
It depends. It's very difficult to say because it will depend.
I just want to know whether there is a relation between this.
I have not seen any such paper or researches so far. I don't know what about Sirshendu because he reads most of the papers. So I don't have an idea, but I don't think so because essentially it will depend on the magma pressure and that heterogeneity of the rock. There are many factors actually. So
true. In that case,
not that whatever relation you are telling. I don't think so. Although I'm not sure.
We have compared actually the dikes of the newer dolerite dikes. So we have calculated this is a tectonophysics paper you can refer to. We have published data. So we have compared the magma overpressure of Deccan with the magma overpressure with the same method of the newer dolerite dikes. So it's definitely much lower in Deccan. So we have only 2 data points, so we cannot generalize the statement. However, the newer dolerite dikes had much higher overpressure calculated from the same method.
What is the and compared to what? Newer dolerite dike
and Deccan.
Okay.
Jyotinwala, but there is a small problem that we are in case of Deccan. whatever we have shown, like in our papers and whatever work we are doing jointly, it is definitely related to the reunion hotspot. Only single hotspot is involved.
That is, I mean, if you think,
But
believe in the
in
hotspot
case
theory.
of Dharwar, be it eastern, be it western, the different ages of dikes, like I was mentioning, there are a total 9 paleoproterozoic dikes, 9 ages have been reported. And with respect to this 9 paleoproterozoic dikes, there are at least 3 plume centers have been identified by Rajesh
Right.
sir and his group. So there are multiple plume centers. So just based on the age, that the younger dikes have lower magma overpressure, I don't think it will fit
No,
so easily.
that's why I said that we have only 2 data points, and I was not talking about Dharwad, I was talking about Shingbum.
Okay.
Yeah. So so newer dolerite dikes, I think they have associated with the same origin, so we can kind of extrapolate this analysis. But I mean, this is only 2 data points, so you cannot generalize the statement.
Yes, but this is a good line of thought. Sirshendu can think of. It's a good line of thought. Sirshendu, you can.
Like there are so many factors acting together, it's difficult to constrain.
This thing can be only thought if we think that they are coming from the same magma pool.
Right, sir.
Definitely.
And that is the problem. For example, in case of Dharwar, where Sirshendu is working, there have been reports of at least 3 plume centers, and which are misplaced far away from your eastern Dharwar. One plume center is on the northern part of eastern Dharwar. One plume center is in the southeastern part of eastern Dharwar. So they are spatially also, they are very much dispersed.
Okay. Okay. Very good. Good work.
Thank you, sir.
So any more question, any more queries, suggestions from the audience? Sumita is there or not?
No, I think Sir has left.
Sir has left?
I think so. I don't know. No, he has not joined again.
No, he joined.
No, he joined. Then he left.
No, he is not here.
Okay, if there is no query,
I think Dilip sir is here, sir.
huh?
Dilip Mukhopadhyay sir is here, I think.
Oh, Chitradurga is there. Okay.
Dilip sir is here.
Sir, you have any suggestion for him? Our young kid? Yeah.
Yes, I could find myself.
Yeah.
Sirshendu's, one thing I'm really impressed is the way you present it.
Thank you very much.
I'm Dilip Mukhopadhyay. I was an IIT rookie. It's said, Ram Jethmalani, for example, every lawyer goes to the same different law colleges, but they are taught the same thing. And the case is same. But a good lawyer and a bad lawyer, the difference is how they put their case. And I'm really glad that you have put your case very in a way that everybody understood what you are talking about, which is a good trait, which is a very good trait. And I wish you remain in academics so that you can teach future generation of students.
Thank you very much.
So everybody has said about your work, so there has been a long discussion. I just want to say something, a small thing. Your dikes, as you projected, I think they are ellipsoidal, right? Like a pancake.
In 3D, they should be ideally ellipsoidal.
Ellipsoidal, or I mean pancake type of kind of situation.
Idli.
Yeah, we prefer.
Approximate.
Yeah.
That depends on how the pancake is made.
If I make, it will be definitely like pancake. If I make a pancake.
So I'm in Kolkata right now. I'll come over to your place to eat your pancake. That you.
Okay, you are welcome, sir.
So if it is that pancake-like, and if your some measurements have that there are only tens of meters, right?
Yeah. Yes.
Tens of meters, and if I assume that there are also tens of meters in the vertical distance,
yeah.
So this is a 10 by 10 kind of an ellipsoid, you know. How deep would be your magma chamber that it will produce an ellipsoidal or flat pancake type of ellipsoid with only dimension of few tens of meters?
Ideally, it should be just below that. I mean, like very shallow chamber. If it is so small, but then it can be an offshoot also. I cannot be sure about it.
Okay, so at that time you think that the magma chamber was at a very shallow depth.
In one location where the magma depth to magma chambers are in the range of 10 kilometer or 12 kilometer per se, definitely they should be at a comparatively shallower depth. Not 10 kilometer below right now, but definitely at a comparatively shallower depths.
10 kilometer at a depth of the dike formation, is that right? And they're together at a 10 kilometer depth.
Like it is the height of the dike above the magma chamber. It is 10 kilometer. That is, it is the diameter of the pancake.
Okay, all right. Okay, I get it. Okay, so it is a good talk, very good talk. I really enjoyed the talk.
Thank you very much, sir.
Okay.
Jyotirma, it's time for you.
Yeah, if there are no further questions, I completely agree with Dilip Mukhopadhyay, sir. I mean, you really presented well. Very well done, Sirshendu.
Thank you very much.
The way you spoke was very nice. You are also very receptive to the suggestions, and that's a good thing. Keep that up. Yeah, so let's give a big round of applause to Sirshendu, and we thank you very much for taking the time out today and speaking to us. So again, just a gentle reminder, please submit your abstracts. The deadline is 31st July. Please book your tickets. Please register to the RDS 8. And I will send the online talks announcement for next month pretty soon. Have a good evening, everyone.
Including
Bye.
the weekend. There's a weekend.
Yes, weekend. Tomorrow is not weekend for me, but yeah, that's why.
For me, so yes.
Yeah.
Okay. Thank you very much.
All right. Take care. Bye, everyone. Bye.
Thank you, Jyotirma.
You are welcome, Sudeep. Bye.